In this training, we'll go into more detail on the 802.11ax standard, including its use of additional spectrum, the 6 GHz, known as Wi-Fi 6E. We will also discuss legacy device benefits in 802.11ax environments and use cases. As you know, the 2.4 and 5 GHz is becoming more and more congested. Not only is there contention from other Wi-Fi traffic, but other sources using the spectrum. Until now, the allocated spectrum for Wi-Fi has been limited to 600 MHz and has not changed for over 20 years, adding to the congestion and constraints. The FCC has allocated a new spectrum in the 6 GHz band, and the Wi-Fi Alliance has included it in the Wi-Fi 6 standard, greatly expanding the range of heavily used Wi-Fi networks. Further, only 802.11ax devices will be able to use this new spectrum, eliminating the need for support of legacy devices within the new band. Because of this new allocation, along with less interference from non-Wi-Fi devices, 80 or 160 MHz channels might now be possible. On April 23rd of 2020, the U.S. Federal Communications Commission (FCC) vote was unanimous to allocate 1,200 MHz of spectrum for the unlicensed use of the 6 GHz band. European unions have designated 500 MHz to the Wi-Fi 6E with hopes of releasing the spectrum sometime in the first half of 2021, with other nations not far behind. With the Wi-Fi Alliance deciding to extend the Wi-Fi 6 standard to include the new 6 GHz band, manufacturers are rushing to the market with APs that support the new spectrum. Wi-Fi 6E is significant in that it represents the first ever expansion of Wi-Fi spectrum. As the number of connected Wi-Fi devices grows by 22% each year, the congestion can downgrade performance in even the best Wi-Fi networks. Traffic overloading is especially problematic in high-density venues like auditoriums and lecture halls. It also is an issue in apartment complexes and other multi-dwelling units, where uncoordinated access points interfere with each other. Legacy bottlenecks, a key to Wi-Fi success and backwards compatibility, is also a big disadvantage. To ensure interoperability, slower 802.11b, G, and N devices are prioritized equally with faster Wi-Fi 6 devices. But when slotted ahead of a faster device, a slower device impedes overall throughput. Theoretically, wider channels translate into faster speeds, so the 80 MHz and the 160 MHz channels supported under the current Wi-Fi standards should offer higher throughputs. In reality, many of these channels are non-contiguous, limiting the wide channel advantage and constraining throughput. In addition, spectrum allocated to the Wi-Fi 6E will address many of these current challenges. Less congestion. Previous Wi-Fi offers 27 non-overlapping 20 MHz channels, while the Wi-Fi 6E will offer 59 new 20 MHz channels. The added channels will alleviate many of the congestion challenges and enable better support for more connected devices and device types. Higher speed. 1200 MHz of contiguous spectrum enables channel bonding of 80 MHz, 14 new channels to be exact, and even 160 MHz, which is 7 new channels. This is good news for high-density venues like convention centers and auditoriums. In the home, Wi-Fi and Wi-Fi 6E will deliver speeds that complement the multi-gig speeds of the latest fiber offerings. By combining multiple 20 MHz channels into a wider, higher throughput 80 MHz or 160 MHz channel, existing Wi-Fi 6 clients can reach their maximum speeds without the limits of operating in smaller channel widths. In the past, these channels have not been feasible due to high utilization of the 2.4 and 5 GHz spectrum. With Wi-Fi 6E, only the 802.11ax devices will be utilizing the new spectrum, eliminating slower legacy device support. Wi-Fi 6E can also support more wired replacement applications like wired point-to-point and indoor mesh backbone links. Lower latency. Wi-Fi 6E will only support OFDMA and multi-user MIMO 1024 QAM. and 6 GHz capable devices. Other legacy Wi-Fi devices will be limited to the 2.4 and the 5 GHz bands. Separating the traffic ensures speed that ultra latency sensitive applications such as augmented or virtual reality and gaming and real-time applications require. New APs are expected to provide backwards compatibility to support Wi-Fi 6E and legacy bands with the device. As a result, Wi-Fi 6E will enable delivery of deterministic, low latency, high reliable quality of service required for the next generation of wireless applications. Although it's exciting that we have new spectrum to use, there are existing licensed services or incumbents within the spectrum, which will need to be protected when 6 GHz is used outdoors in specific locations where they're located. These incumbents include fixed services, fixed satellite services, and mobile services. Other than mobile services, these incumbents rarely change. Therefore, they're easy to avoid and their locations are coordinated with outdoor AP deployments. This results in outdoor APs required to support automated frequency coordination. Chipset manufacturers have already announced their new 6 GHz capable low-power indoor APs have already been announced. Standard power APs for enterprise use are expected to begin around the latter part of 2021. The lag between the two release dates are due to additional requirements of AFC. Any Wi-Fi 6 EAPs that transmit indoors using low power, 30 dBm or lower, are not required to participate in automated frequency coordination activities. As a result, these indoor devices have restrictions on their capabilities and design. These restrictions include not allowed to have weather-resistant enclosures, external antennas, and battery-only operation. Such restrictions prevent equipment manufacturers that create Uni 5 and Uni 7 band supported APs from causing potential interference problems for incumbents. There is a new very low power category identified in the FCC's notice for portable devices possibly providing an option other than Bluetooth as a personal connection, but we will have to see if or how this category will be applied. Standard power indoor or outdoor APs are required to support and enforce frequency coordination, which is automated frequency coordination services. Wi-Fi AFC provides a list of frequencies where the AP can operate safely without interfering with other incumbents like fixed microwave operators. Standard power APs must connect to a cloud AFC database and report their position. The AFC then assigns a specific operating channel for the AP. FCC's 6 GHz R&O and FNPRM, adopted on April 23 of 2020, defines two categories of devices, a standard power access points and low power indoor access points. The R&O describes automatic frequency coordination mechanism that would identify which frequencies are available to unlicensed devices without causing harmful interference to fixed point-to-point microwave receivers. Understand that the 6E is not a new technology, but instead new lanes on the wireless highway that are dedicated to the express devices. Because it is only dedicated to the new standard, only OFDMA will be used, providing high efficiency when forwarding data. As mentioned, legacy devices will not need to be supported, providing faster forwarding and lower latency. Higher frequency does come with a cost, which is less range than the lower frequency counterparts. However, 802.11ax standard supports all three frequency ranges, providing broad support and range and coverage. Regardless of this, 6E with less possible interference will be welcomed spectrum to push the limits of speed and efficiency in Wi-Fi networks. In this section, we'll discuss 802.11ax legacy device benefits and a few use cases when it comes to AX. People ask why I should start purchasing and using 11ax when I have a few 11ax clients today and 90% of the devices are AC. This was the same question that was asked when 11AC came into the picture, as most of the devices were 11N with few being 11AC. There are several reasons to move on to 11AX. First, an 11AX AP can serve both 11AX and legacy clients as backwards compatible. Manufacturers are starting to make 11AX clients now, so over the next several years there will be a lot more AC and AX clients. Secondly, 11AX and legacy clients can coexist just like 11AC and 11N did. And then third, both 11AX and non-11AX clients benefit. 11AX clients will be more efficient and free up more spectrum for 11AC clients. This is like express lanes. The first two lanes are for the 11AX devices. Let's say 50% of the devices are 11AC and 50 are 11AX. I put all the 11AX devices in the express lanes, which makes them more efficient, and the remaining AC clients benefit because I took half the cars from the lanes, which frees up contention for all the 11AC devices. This gives me a higher throughput and performance for my network. 802.11ax will roll out in waves similar to 802.11ac. Wave 2 certification will occur in 1 to 2 years after Wave 1 certification. Wave 1 will include download and upload OFDMA, download multi-user MIMO, and target wake times. Wave 2 will include upload multi-MIMO, spatial reuse through BSS coloring, 160 MHz channels, and 6 GHz long-range operation with AFC support. With the FCC releasing the 6 GHz channels, it opens 1200 MHz of unlicensed space in the 6 GHz range. The advancements of 802.11ax will benefit a wide range of use cases, but particularly important for dense environments in which large numbers of users and devices are connecting to the same network. Some scenarios that will benefit from the advancements in the 11AX standard are large public venues. Stadiums and convention centers are common LPVs that increasingly offer Wi-Fi to improve fan or attendance experiences, increase customer interactions, and create value-added services such as showing instant replays on fans' devices, or allowing attendees to order food from their seats. Stadiums and convention centers with tens of thousands of users all connecting to the Wi-Fi at the same time pose unique scale and density challenges. The 802.11ax advancements around OFDMA, 1024 QAM, OBSS coloring, and the faster PHY rates will make it easier for the large public venue owners to create new business opportunities by offering enhanced services to guests. Transportation hubs. Public transportation stations also offering public Wi-Fi. Like stadiums, transportation hubs have high densities of people attempting to connect to the network simultaneously. However, these hubs face unique challenges posed by transient devices that are not connecting to the Wi-Fi network but are still sending management traffic that congests it. In 802.11ax, advancements with OFDMA and BSS coloring provide tools to manage the challenge with these dense environments. IoT and smart city deployments. These deployments face a wide variety of challenges. In some cases, there can be high volume of devices all attempting to communicate simultaneously, such as at a manufacturing site. In others, a small number of devices could be idle and need to phone home once a day. Power efficiencies in 802.11ax can enable devices to go into deep sleep mode and turn their transmitters at predefined intervals to prolong field time without maintenance. Education. College and university campuses have high densities of Wi-Fi users in areas such as libraries, auditoriums, lecture halls, and student unions and student housing. Primary K-12 education tends to use video-based learning, one-to-one computing, connected classrooms, and IoTs are creating airtime capacity crisis, which stresses the network's reliability. With additional spectrum for Wi-Fi and with all the new 802.11ax features, we can see that Wi-Fi is expanding to meet the demand and exciting to see 6 GHz Wi-Fi transmissions in the near future.